Today we want to look at a pretty interesting product of values of the cosine function. In particular, the product as k goes from 1 to n of cosine of k times pi over 2n plus 1. So often when you're working with a product, infinite or otherwise, you generally want to transform it into a sum by using properties of the logarithm, and that's exactly what we're going to do here. So let's take the log of both sides and see what this looks like, and that's going to motivate the next couple of steps. So taking the logarithm, well, like I said, that product will turn to a sum. So we have the sum as k goes from 1 to n of the log of the cosine of k times pi over 2n plus 1. Okay, so like I said, that maybe motivates us to look at something that we see inside of this sum. In particular, we're going to look at this nice formula for the log of the cosine of x. And this is like maybe what we would call the Fourier series for this, although you don't really need to know anything about Fourier series for the development of this formula. So that being said, let's see how we can develop, well, I haven't written the right-hand side of the formula, but how we can develop this formula that we'll see for the log of the cosine. Okay, so we want to start with the following formula, and that is the cosine of 2mx is equal to 1/2 times e to the I 2mx plus e to the minus I 2mx. And here we're using Euler's famous formula for the complex exponential, that e to the I theta is equal to cosine theta plus I times sine theta. And of course, you can use e to the minus I theta is equal to something similar, and then the evenness and oddness of cosine and sine respectively will help you gain this formula. Okay. So now we're going to take an infinite sum of what we have right here. Well, not exactly, but an infinite sum built out of these parts. So let's look at the sum as m goes from 1 to infinity of minus 1 to the m over m times this cosine of 2mx. And well, what's our motivation here? Well, observe that the sum as m goes from 1 to infinity of minus 1 to the m over m is related to the logarithm. That's kind of a famous result. And we won't explicitly use this here. We'll develop that into our construction here. But that's at least a motivation for, using what we've got up here to develop this log cosine formula. Okay, so now let's write this as 1/2 times this sum as m goes from 1 to infinity of minus 1 to the m over m times, let's see, e to the I 2mx, the sum of the next part as well. So we've got m going from 1 to infinity, minus 1 to the m over m, e to the minus 2I mx. And now we could use just a standard known formula for these sums in terms of logarithms, although I'd like to maybe not use those and go from something a little bit more familiar. And how we'll do that is as follows. I can write this whole thing as 1/2, and then this first bit I can write as the integral from 0 to e to the I times 2mx of, let's see, it's gonna be the sum as m goes from 1 up to infinity of minus 1 to the m times t to the m minus 1 dt. So observe, if I take the antiderivative of this, I get t to the m over m, and then I can evaluate this from here to here, and we'll get exactly this expression. But observe, I made a bit of a mistake here. That should be e to the I 2x. And then we're raising that to the nth power in the end. Okay, and now we're going to have something similar for this up here. So let's see, plus a half, and then we've got our integral from 0 to e to the minus 2ix. And then our sum, as m goes from 1 to infinity, of minus 1 to the m times t to the m minus 1 dt. Okay, great. But now what I'll do here is I'll factor a minus sign out of that. That'll turn this mth exponent of minus 1 to m minus 1. I'll do the same thing here, and we'll have an m minus 1. And then we have geometric series in there. So let's see, that'll leave us with minus 1/2, and then we have our integral from 0 to e to the I 2x of 1 over 1 plus t dt for this first one, just using a standard geometric series summation technique. And then, well, the same thing over here. So minus a half, and then we have our integral, 0 to e to the minus I 2x, and then 1 over 1 plus t dt. But of course, the antiderivative of 1 over 1 plus t is the natural log of 1 plus t, or the log of 1 plus t. So plugging in those endpoints, we'll see that we get the log of 1 plus e to the I 2x for this first one, and then the log of 1 plus e to the minus I 2x for this second one. And there I factored that minus sign out. Okay, so now what could we do? Well, we could use logarithm rules to push these two logs together, keeping in mind that we're going to get the product. Okay, so that's going to leave us with a minus half and then a log of the product of these two terms. But let's see, 1 times 1 is 1, e to the I 2x times e to the minus I 2x is also 1, so those will sum to 2, and then we'll get the cross terms, which in this case are e to the I 2x plus e to the minus I 2x. Okay, cool. But notice that looks exactly like a formula we used up here in our first step, just without the m. And so in fact, this sums to 2 times cosine of 2x. Okay, so now we have this sum right here that we started with is minus a half log 2 plus 2 cosine 2x. So let's start from there and see where we can go. Okay, so here's where we left off, and now we're ready to start putting it back together. And now we're going to use maybe a power reducing formula in reverse, or a double angle formula, to simplify this 2 plus 2 cosine 2x. And that's going to simplify to 4 cosine squared x. And then, well, we can use logarithm rules again. And that's going to end up leaving us something like this. Minus the log of 2. So that's from minus a half times the log of 4. The half comes in and takes the square root. And then we'll have minus log of cosine of x for, essentially the same kind of reason. So that means, well, we can go over here and solve for log cosine x. And observe we're going to get minus log 2. And then from that, we subtract. The sum as m goes from 1 up to infinity of minus 1 to the m over m times cosine 2mx. And there we have it. We have our Fourier series for the log cosine. Now, that being said, let's see how we can apply that to our goal. Okay, so using this tool again, let's recall that our product, we can take the logarithm of our goal product and it turns into the sum of those logs like we talked about before. And now I'll replace this log of cosine k pi over 2n plus 1 with this formula right here. So let's see, that's going to end up giving us the sum as k goes from 1 to n of minus log of 2, and then minus our sum as m goes from 1 up to infinity of minus 1 to the m over m, and then we'll have cosine of, well, 2mx, but now x is that stuff in there, so that's going to be 2m k over 2n plus 1. So we've got something that looks like this. But now let's split this sum inside of the sum into two cases. And those cases will be when m is a multiple of 2n plus 1 or not. But before we do that, let's observe that this first bit is fairly easy to sum because we're just adding negative log 2 to itself n times. So let's bring that out. So we'll have minus n times log 2, and then we'll have minus the sum as m goes from 1 up to infinity of the sum as k goes from 1 to n of this cosine thing. So I switched the order of summation there, but that's totally okay. We don't even need a theorem for that because this is a finite sum. Then I'm going to actually split this into two parts. So let's get it written down first. And well, that's essentially just writing the same thing twice. Great. But of course I can't just write it twice. What I'll do is I'll say that in this first one, we have m is a multiple of 2n plus 1. But observe that if m is a multiple of 2n plus 1, then that means that the 2n plus 1 in the denominator will be canceled. And in fact, what we have is an even multiple of pi inside of the cosine. But an even multiple of pi inside of the cosine is exactly equal to 1 by the 2 pi periodicity of the cosine function. So this gives us a 1 here. And then we have to look at this next case as well, which is a little bit trickier. So this is when m is not a multiple of 2n plus 1. That being said, let's bring down what we have first. So we've got minus n times log of 2, and then minus the sum as m goes from 1 to infinity, where m is a multiple of 2n plus 1. So I can encode that as follows. Minus 1 to the m over 2n plus 1 times m, just by a little bit of re-indexing. So let's observe that that's adding over all of the multiples of 2n plus 1. Well, in this next case, we're going to get something a little bit trickier, like I said. So I'm just going to bring down our sum as m goes from 1 to infinity, minus 1 to the m over, now we just have an m in the denominator. And now I'm going to write, well, what that sum ends up being. Now, I'm going to use this little fact right here that this cosine of 2m times k times pi over 2n plus 1 is, well, it's going to be equal to 1/2. And then I'm going to write this as omega to the mk plus omega to the minus mk. And this is going to be when omega is equal to e to the I times 2 pi over 2n plus 1. So in other words, omega is a primitive 2n plus 1 root of unity. But now we're adding when m is not a multiple of 2n plus 1. So that's actually going to give us every power of omega in here, maybe in just a different order, except for omega to the 0. So in other words, we have something like this. We'll have omega plus omega squared all the way up to omega to the 2n. And I need to bring that half out, which is from this half right here. Again, those are just permuted a little bit. But since omega is a 2n plus 1 root of unity, we know that if we were to add 1 to this, we would get 0. But if we add 1 to that and get 0, then that means that this whole thing must sum to -1. But that means that that -1 can be brought up here, turning this into a plus, and then we can just scrub this part away right here. And then I guess I should decorate this down here where this is m equals not a multiple of, let's see, 2n plus 1, because that rule comes down from the previous step. But now from here, what we'll do is try to push these two sums together. But notice that this first bit is adding over all values of m, and these are all values of m that are not multiples of 2n plus 1. But now what we'll do is add back in the multiples of 2n plus 1 to this sum. Okay, so that's going to give us the following. We'll have minus n times log 2. And then if we add them back into this sum, then that means we need to subtract them. Well, let's subtract them from this sum. But when all is said and done, that's going to leave us with a 2n plus 1 over 2 out front. And then we've got this sum as m goes from 1 to infinity minus 1 to the m over 2n plus 1 times m. And then we have this plus 1/2 times the sum as m goes from 1 to infinity of minus 1 to the m over m. Again, I got rid of this green underline note here by adding in the multiples of 2n plus 1 to our values of m, but then I subtracted them off, and I subtracted them off into this sum. And that gave me this coefficient out front. Okay, cool. But now, well, let's observe that we get some simplification. This 2n plus 1 will cancel this 2n plus 1, and after that, this whole sum will cancel this whole sum, leaving us with this thing being n times the log of 2. So let's put that way up here. So we've got our product. Well, the log of our product is equal to this minus n times log 2, but using logarithm rules, we have the log of 2 to the minus n. But then exponentiating both sides, well, we have our value. We have our product is equal to 2 to the minus n, in other words, 1 over 2 to the n. And that's a good place to stop.